Okay, welcome to what I'm calling the Octave or the MATLAB tutorial for Unit 1 for this class. And what I wanted to do today was show you how I generated the direction field, the plot for the direction field in MATLAB or Octave from Lecture 8 of Unit 1, which is right at the end of Week 2. So in that lecture, we were looking at the ODE, dy by dx equals 0.2 times xy, which was a separable ODE, so it could easily be solved to find the exact solution. Okay, so what I plotted in that class was the direction field, which are these purple arrows here, or the pink arrows, and I also plotted a couple of solution curves, which are the black lines here. So I wanted to show you in Octave how we can generate this direction field. Okay, so I'm going to use Octave Online today, so octave-online.net. So if you want to use Octave Online, navigate there now and sign in using the menu on the top right. Okay, so I'm already signed in, so that's good. So everything I do today will translate over to MATLAB. So just because I'm using Octave, you are more than welcome to use MATLAB. Not a problem at all. Okay. So all my files in my Octave Online Octave Online are stored on the left here. If you recall, we wrote this new to Octave file last time in the last Octave tutorial, and well, maybe let's just run that and see what it did. So we should get a plot of log of x plus 2, which is here. We should solve this algebraic equation, so we solved that here, and we did a little bit of matrix multiplication. So, okay, so the reason I ran this file is I wanted to show you something. When your command window is full of junk that you don't want anymore, we can type into the command window CLC, and what that stands for is clear command window. So now we start with a blank slate. So what I want to do is generate a new file. Okay, so this button up here, this piece of paper with a plus, generates a new file. And I'm going to call it direction field plot. Notice that the extension is .m, the file extension is .m. Okay, so this is telling me that it's essentially using the same format as MATLAB files. So anything we write in this Octave file, well, pretty much anything will translate directly over to MATLAB. Okay, so to start my file, it's often a good idea to clear everything that is on your workspace. So you can see in this VARS here, this variables, because I ran this other code new to Octave, I have some variables stored in my memory, A, B, answer, and X. So what I'm going to do, I'm just going to type clear all, and if I save my code and run it, that should clear these variables here. Good. I also want to close any figures that are open, just so that we don't have a mess and storing figures everywhere. So I'm going to type close all, and again I want to start with a blank slate, so I'm going to type CLC. Okay, but what I actually want to do is I want to open a new figure. I want to type hold on because I want to plot more than one thing on this figure, and I want to generate this direction field. Okay, so if I just ran this code as it is, I generate a figure, or let's say a set of axes, which is not very interesting. So the first thing I want to do actually is add an x and y axis. So I'm just going to type the commands for that now, and then I'll explain what each command is doing. Okay, so these first two commands are plotting the x and the y axis. Okay. Get this mouse pointer out of the way. So the first line here is plotting a point between x equals 0, y equals -5 to x equals 0, y equals 5. it takes the point 0, -5, and draws a line between that point and 0, 5. And then similarly, the second line here takes a point between x equals -5, y equals 0, and draws a line between that point and x equals 5, y equals 0. Okay, so if I do that now, I can see that I've got my y and my x axis drawn on this figure. Sometimes I might want to change the range of this axes, so maybe I want to make the axis line up with the ends of these x and y axes. So at the moment it's going from -6 to 6, well really I want it to be -5 to 5, so I can change that by going axis and then entering my x value. So I want my x values of the x-axis to go from -5 to 5. And then I want my y values to go also from -5 to 5. So then if I plot that, save and run that, you see now my axes line up nicely with the edges of the axes. Okay, good. Okay, so now I can start thinking about plotting the direction field. The first thing I want to do is generate a set of coordinates which I'm going to call capital X and capital Y. Well, maybe at I want to generate a grid on this axis that is, or this figure that I've just created. So maybe I want to plot a point at every full numerical step. So for example, from -5, -4, -3, -2, -1, 0, all the way through to 5. And then similarly in the y direction, 0, 1, 2, 3, 4, and so on. The way I do that, the way I generate a grid, is I use this command mesh grid. Okay, and I say I want to generate a grid that's going from x and y equals -5 and steps of 1 all the way through to 5. Okay, and if I run that, save and run that, let's see if I get any issues. Okay, great. So I get a set of points x and y. So this is actually a matrix now. So if you think of these, the first entry in x here, the 1, 1 entry in x, and the 1, 1 entry in y, that's point -5, -5. Okay, or if you go all the way down to the bottom, so in the first column, the last entry, x equals -5, y equals +5. So this is a set of points. These matrices represent a set of x values and a set of y values. So when we take these together, they represent a set of coordinates. So what I'm going to do, I'm going to suppress the output of this because I don't want to generate this XY matrix every time. So if I add that semicolon, that suppresses the output. It doesn't write it. And what I'm going to do is just to show you these points on the graph. For now, I'm just going to plot x, y as a dot. So you can see here that my grid or this command mesh grid is generating a point at each one of these dots. So from x equals -5 to 5, from y equals -5 to 5. Okay. So these are the points at which we're going to plot our direction field. Okay, well this is kind of ugly, so I don't really want to plot that, but what I might do is just put a percentage sign next to that command. And if I save and run that again, you'll see that now it doesn't plot this command here. Okay, so the percentage sign is basically for commenting. Okay, so this is, if I want to comment, I could say, well, this generates a grid to use in our direction field. Okay, so you can comment your code, which is always a good idea. For a tutorial like this, it might take me too long, so I might not comment everything. Okay, so now I've got a grid with grid points capital X and capital Y. the next thing I want to do is I want to generate the left-hand side of this differential equation. Okay, so the left-hand side of the differential equation was 0.2 times x times y. So what I'm going to call that is S, because really what that right-hand side of that first order ODE was telling me was the slope of the direction field at that line, at that point, right? So, okay. Okay, so what I've written here is S representing the slope of the ODE at the points x and y. So now recall that x and y are matrices, okay? So if I type over here capital X, X is a matrix. So if I simply write x times y, x star y to represent x times y, what this actually gives me is the matrix multiplication of x and y, okay? Which is not what I want. What I actually, if you look at x and you look at y, what I actually want for this right-hand side of this differential equation is to take the entries in x and multiply them by the entries in y. So negative 5 times negative 5 is positive 25. When I just wrote x times y, I got this weird thing 110. Okay, and that's because this tells MATLAB or Octave do the matrix multiplication of x and y. But that's not what I want. What I want is the term by term multiplication, the multiplication of term by term in x and y. And so the way that MATLAB and Octave recognizes to do that is instead of doing x times or x star y, we do x dot star y. Okay, and the dot tells MATLAB to perform term by term or entry by entry multiplication of these in this matrix, in these two matrices. So that is why on this left-hand side here, I wrote the slope is equal to 0.2 dot times x dot times y. Okay. So, well, if you didn't learn this in first year, now's a good time to well, let's say refresh. Okay, so I can generate a direction field from this slope data. And so the command for doing that is quiver. Well, in fact, before I do that, let's come down to the command window here. Let's just say I knew there exists this command quiver, but I didn't know how it worked. Okay, so what I can do in this command window is I can type help quiver. Okay, and that will bring up all the documentation for this function quiver. And so see what quiver is telling us here is we have an x, y, a u, and a v entry. And if we read the instructions down here, the u and the v are components of a vector field at the grid points x and y. So x and y determine the point to plot your direction field. U and v basically tell you well, essentially the slope, right? So what I can do here is write x, y, u is the x slope, v is the y slope. So what I can do is here just write 1 and s, and we'll see if what that does. They must be the same size, so let's say, okay, 1's size s. So what this command is, 1 size s, it generates a matrix of 1's at the same size as that matrix S. So if I do that here, I get this direction field plotted. Okay, and this is awesome. This looks great. This is doing exactly as I'd hoped. But you might notice that it is a little bit different to the one that I plotted the other day. Okay, so the difference actually is that I normalize my direction field here so that all these vectors were the same length. Okay, so I haven't done that here. I've let steeper arrows be longer and shallow, let's say horizontal arrows be shorter. So if the slope is 0 or close to 0, then my arrows are shorter. Okay, I can normalize these if I want to. So let's do that, just so that we know how to do both. So L is equal to the square root of 1 plus s squared. S is the slope, capital S. And again, I'm using this dot and then this to the power of sign 2. So I have to use this dot to tell me to do element by element squaring. So this is essentially s dot times s. Okay, so this is L is basically giving me the length of each of these vectors here. So now instead of plotting this vector of 1s, I can just plot L. And if I do that, I get something that should have been plotting at the same size, but I must have a problem here. Ah, right, yes. So it should be, this actually should be 1's size s dot divided by L, because I'm normalizing by L. So actually, I need to normalize s by L as well. So now if I save that, I should get something that looks pretty similar to what I plotted the other day. Okay, so the arrows are a little bit longer than I plotted the other day. So let's see if we can fix that. Help quiver. Let's see if our help will. Okay. So we have an optional input s, which is a scalar, defining the scaling factor. So what we can do here in theory is after we've entered these 4 entries, x, y, this normalized set of 1s, and then the slopes, the normalized slopes, in theory we can just change this number, which is default 0.9. So if I change that to 0.25, that should shorten my arrows a little bit. And it does, so that's good. Okay, so I've generated a direction field here for that plot. Maybe we should add a title actually. So let's go title direction field for dy by dx equals 0.2 xy. And maybe we should add a x label, so an x-axis label. Let's just call it x. And let's do the same for y. Okay, so that should give me a title and label my axes, which is always a good idea. X, Y direction field, good. Okay, good. And then let's plot some solution curves on top of this graph here. So, okay, so the exact solution that we were looking for was y of x equals some constant times the exponential of 0.1 times x squared, right? Okay, and similar to last time in lecture 8, let's plot two of these solution curves when c0 equals 0.3 and then also when c0 equals negative 0.3. Okay, so what I want to do here is I want to generate a set of x values. So I have a matrix of x values, but I just want a line of x values now, okay, which is basically the line that we use to generate the x-axis here. So let's just go x vals equals negative 5 in steps of, well, let's say 0.1 through to 5. So this will generate a vector of x values, so from negative 5 all the way through to positive 5 in steps of 0.1. And so we can plot that solution curve on top of our direction field. Okay, so we're going to plot the x component of the plot, we're going to plot x vals. Okay, and the y component of the plot is the exact solution over here, right? So for c0 equals 0.3, it's going to be 0.3 e times exponential of 0.1 x squared. So 0.3 times the exponential of 0.1, wasn't it? Yeah, 0.1 times x squared. So x vals squared. And let's plot that in green. No, not green, that's a bit yuck. Let's plot it in magenta. Okay, great. So there is our direction field, and on top of that direction field we have this lovely magenta solution curve. Let's do the exact same thing for the case when our integration constant was negative 0.3. Great, so there we've got our two solution curves. And so this is basically where we were in lecture 8. We have our direction field and our two solution curves plotted. But this looks a little bit stretched in the x-axis, okay, so it still doesn't look quite right. So the one thing command I can add to fix that is this thing called axis square. Okay, so that gets rid of that squashing of that y-axis and the stretching of the x-axis to make them make the plot be a square, which is what we want because the x and the y-axis were the same length anyway. So I could open my plot window at the top here and export this as a PNG file, as an image file, and well, let's see, it should be relatively high quality. Well, okay. You might think that I've lost all the x-axis labels here, but if you zoom in, if I can zoom in fact I haven't actually lost them, they're just in this horrible, really light grey color, which is hard to see. When you paste this, when you copy and paste this into a Word document or some other kind of document, you should be able to see the X and the Y axes labels. If you don't, well, hit me up and we can fix it. Okay, but anyway, we've now plotted the direction field for dy by dx equals 0.2 xy, just like we did in class, and we've also plotted the two solution curves. Okay, so you might, well this should hopefully be helpful for your assignment. But the other part of your assignment is solving differential equations using the built-in solver in MATLAB or Octave called dsolve. So what I'm going to do in my code here is I'm just going to clear all the variables I've generated so far. Okay, I'm not going to touch the figures, so I'm not going to say close all. I'm not going to say CLC because I still want to be able to see this figure when it's generated. I'm just clearing the variables here, okay? And what I'm going to do is I'm going to generate a new variable called y, which is a function of x. So typing y and then putting x in the brackets here tells me that y is a function of x. Okay. I'm going to define my differential equation. So dE equals differential equation. I'm going to define this as taking the derivative of y of x with respect to x. I'm going to subtract from that 0.2 times x times y of x equals 0. So here all I've done is I have rewritten my differential equation from the other day, dy by dx equals 0.2 times x times y. I've just taken the right hand side, subtracted the right hand side from both sides of the equation, so I get dy by dx minus 0.2 xy equals 0 on the right hand side. MATLAB and Octave just seem to deal with this better if we do that. Let's just save and run that just to see what happens. Okay, it takes a little bit longer to do the symbolic calculations, but basically here we have dy by dx of negative 0.2 1 over 5 x times y here equals 0. Okay, great. I don't want to output that every time, so I'll put that semicolon. Okay, so the solution to this differential equation is equal to, well, I can use this command, this built-in command called dsolve. So I'm going to dsolve the differential equation. Okay, so if I save and run that, then hopefully it should solve my differential equation. We're running out of time here. Okay, great. So it doesn't actually make it look very pretty here, but what you can see is the it's telling me that the solution is y of x is equal to some constant c1 times e to the x squared over 10. Okay, so 1 over 10 is 0.1, so here we actually have c1 times the exponential of 0.1 x squared, which is, of course, exactly what we found the other day. So we can use MATLAB or Octave to solve our differential equations for us. Okay, so, well, it doesn't really, in MATLAB actually, it presents this solution much nicer on the screen than it did in Octave, but okay, the solution is correct in Octave, so, well, seeing as Octave's free, we can live with that. So let's now solve this same differential equation with an initial condition. So I'm going to call it Sol1, so solution 1. And, well, what's my initial condition? Well, let's use the initial condition when x equals 0, y equals 0.3. Okay, let's use that initial condition. So here I'm going to do desolve again, and I'm going to desolve the same differential equation that we solved before, but now I'm going to write y of 0, so when when x is equal to 0, y is going to be equal 0.3. Okay, we have to use the two equals just because of the logic in MATLAB, but so we're saying when x equals 0, y is exactly equal to 0.3. Okay, so if I save and run that code now, let's hope that it works, otherwise I'll be embarrassed. Takes a little time. You only have a limited number of seconds, so sometimes it says add 15 seconds, so I can do that down here. Okay, good. So, well, we still have the solve before. We just solved the differential equation with no initial condition, whereas down here Sol1 was our initial value problem. Okay, so Sol1 is telling us that y, when x equals, with the initial condition, x equals 0, y equals 0.3, the solution to the initial value problem is 3 over 10, or in other words 0.3, times the exponential of x squared divided by 10. Okay, which of course is what we got before, and we could plot we could generate Sol2 of course as well. Solve the differential equation with the initial condition x equals 0, y equals negative 0.3. So I'll save and run that. So I imagine I'm going to have to add some time down here. So as the time runs down on Octave Online, we wait for the add 15 seconds to pop up, and we'll add a bit of time. And so see here we get the solution to the ODE and the correct solution to the two initial value problems. So this seems to be working perfectly, in fact. We get some warnings here, but okay, they're not too critical for what we've done so far. So one of the places where Octave does actually fall down a little bit compared to MATLAB is we can only solve differential equations symbolically. So there is a slightly different way to solve differential equations using MATLAB, which you can find in the MATLAB study guide. But the method I've introduced here will work for both Octave and MATLAB. Okay, so this is we could say a general way of solving these ODEs, whereas there is also a different way in MATLAB in the MATLAB study guide, which you may like to check out. Okay, the last thing I would point out is that, well, maybe we want to plot this exact solution. So or let's say plot these the solution to these initial value problems. So what we could do is we could just simply write out this equation. Okay, so with the values of x. So well, let's generate a new figure actually, and hold on. And what we're going to do is we're just going to plot the x values we generated before, so x from -5 to 5 in steps of 0.1. Oops, x values. And now we're going to plot the y solution 1 here. So 3 over 10, 3 divided by 10, multiplied by the exponential of x squared divided by 10. So x vals squared divided by 10. And well, let's plot that in a different color. Let's do red. Okay, so now if I save and run this, again I'm going to have to add extra time down here because of this Octave Online limitation. So when the seconds get low, I add 15 seconds. That should be enough to hopefully plot something. So okay, well, okay, I did actually clear my vector x val, so let's copy that down here and rerun that code with the x values added here. I need to give myself some more time in Octave Online. I don't know how many times you can do that. Okay, but here is the plot of of 3 over 10 exponential of x squared over 10, which is from before. And we can also, on the same graph, plot the solution 2, which was negative 3 over 10 exponential of x squared over 10. So negative 3 over 10 exponential of the x value squared over 10. Also plotting an r. Let's also plot this on the same axis range and actually axis square as well. Save and run that. Again, Octave Online, I'm going to have to add some more server time. And that should hopefully be enough to have our plots. Okay, great. So this looks pretty similar to what we had before, just without the direction fields. Okay, so now we've seen how to plot direction fields and solution curves if we've solved this equation analytically. But even if we haven't found the solution analytically by separation of variables, we've shown that using Octave or even MATLAB, we can use this command dsolve to find the exact solutions for any given initial condition. Okay, so you'll notice in both part 1 here and part 2, the thing that really changes for any given problem is the differential equation, or the right hand side of the differential equation. So this is what I was calling slopes. So this is really the right hand side of the ODE, i.e. the slopes. So for a different differential equation, we would obviously change this this line here, right? And for a different, in the second part 2, for a different differential equation, we would change the DE, or differential equation. For a different initial condition, we'd change our initial conditions, right, in dsolve. I hope that was helpful to you. If you have any questions, please get in touch. And I would just like to point out that at this stage, we have covered all of Unit 1. And in fact, if I look at the assignment 1, if I drag that into our window here, if I look at assignment 1, you should be able to complete questions 1, 2, 3, and 4. Those questions all cover topics from Unit 1. And also, going down to the MATLAB questions, you should also be able to solve question 10 in MATLAB. Okay, the rest of the questions are going to be based on Unit 2 material. But my strong suggestion to you would be to start doing questions 1 through 4 and question 10, just to get ahead and to have lots of time to ask questions if you need to. Okay, thank you very much, and I'll see you in the next lecture.